should the randomness decide whether an airbag actually deploys. We explain how the randomness get into the programming and how Selmo takes it out again. For a machine to know what to do, it needs a controller. The controller and the machine exchange digital signals. These are zeros and ones in certain sequences, so-called bit patterns. In order for the controller to know which bit patterns to send, a program is needed. For the program, the programmer describes the desired logical sequence and defines states and state transitions. This creates a fictitious image of the machine states. Since program and machine both represent an actual situation, they do not always match. In order to detect error states of the machine, the programmer must therefore describe them in the program. The problem, the sum of all possible bit patterns doubles with each additional signal. A large part of the error states therefore remains undefined. The result, a program that displays only those errors that have been programmed. The rest is random. We eliminate chance by digitizing the construction of the switching logic. Our role model, automation, when there was no software. Back then, the switching logic of a machine was predefined in a circuit diagram. This meant that each circuit could be checked against a specification. With the Selmo solution, we adopt this sequence. A structured mapping of the function is created from the process model. Then the program is derived from it, automatically instead of manually. The sum of all bit patterns output by the machine corresponds to the permitted states. All other bit patterns are automatically defined as not allowed. This means that all error states are described, and any deviation can be detected at any time and diagnosed beyond doubt. Selmo, for software that never lets you down.